Download this code from codegive.com, link in the description below. I can't provide you with a tutorial on debris risk in space shorts vijetagkstudio because the specific topic vijetagkstudio seems unrelated to space debris and potentially refers to unrelated content or a person. My purpose is to give helpful and harmless information. However, I can give you a comprehensive tutorial on space debris risk assessment and mitigation, including code examples for basic debris modeling and collision probability estimation. This will cover many of the aspects that would be relevant if you were studying space debris issues. Tutorial: Space Debris Risk Assessment and Mitigation. 1. Introduction: The growing threat of space debris. Space debris, also known as space junk or orbital debris, is any non-functional human-made object in orbit around the Earth. This includes defunct satellites, spent rocket stages, fragments from collisions and explosions, tools lost during spacewalks, and even flecks of paint. The problem is that these objects orbit at very high speeds, averaging around 7 to 8 kilometers per second in low Earth orbit, LEO, making even small debris particles incredibly dangerous. A collision with a piece of debris as small as a marble can disable or destroy a satellite. Larger objects can cause catastrophic fragmentation events, creating even more debris in a cascading effect known as the Kessler syndrome. Why is space debris a problem? Threat to active satellites. Debris directly impacts the operational lifespan of valuable satellites used for communication, navigation, weather forecasting, scientific research, and military purposes. Risk to human spaceflight. The International Space Station, ISS, and other manned spacecraft must actively avoid collisions with debris. Astronauts also face a risk from micrometeoroids and small debris. Cost implications. Collision avoidance maneuvers are costly in terms of fuel and mission operations. Damaged or destroyed satellites lead to financial losses and potential service disruptions. Long-term environmental impact. The orbital environment is becoming increasingly congested, potentially hindering future space activities. 2. Sources and types of space debris. Defunct satellites. Satellites that have reached the end of their operational lives but remain in orbit. Spent rocket stages. Upper stages of rockets that have delivered their payloads to orbit. Fragmentation events. The most significant source of new debris. These events occur when satellites or rocket bodies collide with each other or are intentionally or accidentally exploded. Example: anti-satellite, ASAT, tests. Mission-related objects. Objects released during normal satellite operations, such as lens caps, deployment mechanisms, and fragments of insulation. Small debris particles. Micrometeoroids and small debris fragments that are difficult to track but can still cause significant damage. 3. Space debris tracking and cataloging. Organizations like the U.S. Space Force, formerly U.S. Strategic Command, and the European Space Agency, ESA, actively track and catalog space debris objects. Tracking methods. Ground-based radar. Used to track objects in low Earth orbit, LEO. Optical telescopes. Used to track objects in higher orbits, such as geostationary orbit, GEO. Cataloging. The tracked debris is catalogued, and orbital parameters, example semi-major axis, eccentricity, inclination, right ascension of the ascending node, argument of Pareto size, and mean anomaly, are maintained. This allows for the prediction of future positions and potential conjunctions, close approaches, with active satellites. 4. Space debris risk assessment. Risk assessment involves evaluating the probability and severity of potential collisions between space debris and operational spacecraft. Collision probability estimation. The probability of a collision depends on factors such as debris population density, the number of debris objects in a particular orbital region, relative velocity, the speed at which debris and spacecraft are approaching each other, object size and shape, the cross-sectional area of the objects involved, encounter duration, the amount of time the two objects are in close proximity, error in orbital data, uncertainties in the tracked orbital parameters of both the debris and the satellite. Conjunction analysis, this process involves monitoring the predicted orbits of tracked debris objects and identifying close approaches, conjunctions, with active satellites. If the predicted probability of collision exceeds a certain threshold, a collision avoidance maneuver may be necessary. Damage assessment, if a collision occurs, the extent of the damage will depend on the size, mass, and velocity of the debris, as well as the materials and design of the spacecraft. 5. Space debris mitigation strategies. Mitigation involves preventing the creation of new debris and removing existing debris from orbit. Prevention of new debris. Passivation, depleting stored energy sources on defunct satellites and rocket stages to prevent accidental explosions, example venting residual propellant, discharging batteries. Deorbiting, bringing defunct satellites and rocket stages down into the Earth's atmosphere to burn up. This can be achieved through controlled re-entry, actively maneuvering the object for a targeted re-entry. Atmospheric drag enhancement, using deployable sails or tethers to increase drag and accelerate decay. Collision avoidance, performing maneuvers to avoid collisions with tracked debris. Mission design, designing spacecraft and mission profiles to minimize the generation of debris. For example, using tethered deployment systems rather than explosive separation. Active debris removal, ADR technologies and methods to remove existing debris from orbit. This is a challenging and expensive undertaking. Examples include tethered deorbiting, capturing debris with a tether and then using the tether to deorbit the object. Robotic capture, using a robotic arm to grapple and deorbit debris. Net capture, using a net to capture debris. Drag augmentation, attaching a large drag sail to debris to accelerate its decay. Laser ablation, using ground-based or space-based lasers to ablate the surface of debris, slowing it down and causing it to re-enter the atmosphere. This is controversial due to potential weaponization. 6. Code examples, Python. Disclaimer *, these code examples are simplified illustrations and are not intended for real-world operational use. Real-world space debris modeling requires highly accurate orbital propagators, detailed debris models, and sophisticated statistical analysis. Libraries like Orbital or Astropy are often used for more precise calculations. Example 1, Basic Orbital Propagation, Simplified. This example shows a very simplified propagation of an orbit. It uses Keplerian elements and doesn't account for perturbations. Important considerations for the propagation code simplifications this code is extremely simplified. It does not account for perturbations real orbits are affected by gravitational forces from the Sun, Moon, and other planets, atmospheric drag, especially in LEO, and non-spherical Earth effects, J2 perturbation. These must be considered for accurate long-term propagation. Coordinate systems this example assumes an Earth-centered inertial, ECI, Coordinate system. You need to understand and use appropriate coordinate transformations for real-world applications. Real-world tools. For accurate propagation, use libraries like Orbital. A powerful open-source space dynamics library written in Java, with Python wrappers available. Astropy. A Python library for astronomy with some orbital mechanics capabilities. SGP4/SDP4 algorithms widely used for propagating orbits from two-line element, TLE, data. Example 2, simplified collision probability estimation, P sub C/sub. This example provides a very basic illustration of collision probability, based on the idea that the volume occupied by the satellite and the debris must overlap. This is a gross oversimplification, and much more sophisticated statistical methods are used in practice. Key limitations of the collision probability example simplified geometry This model assumes spherical objects and doesn't account for the actual shapes of satellites and debris. Static density The volume density is assumed to be uniform and constant. In reality, debris density varies significantly with altitude, inclination, and other orbital parameters. Error covariance The biggest simplification is the lack of error covariance modeling. Real conjunction analysis uses the uncertainties in the position and velocity of both the satellite and the debris object to compute a more accurate collision probability. The position and velocity boxes become probability distributions, usually Gaussian, and the collision probability calculation involves integrating the overlap of these distributions. This is much more complex. 7. Tools and resources. SpaceTrack, spacewatch.org a primary source for TLE data and conjunction analysis reports. Requires registration and acceptance of terms of use. NASA Orbital Debris Program Office provides information and resources on orbital debris. ESA Space Debris Office provides information and resources on orbital debris in Europe. Stock, Systems Toolkit, by AGI, ANSYS a commercial software package widely used for space mission analysis, including debris modeling and collision avoidance. Orbital open source space dynamics library, allowing for advanced orbital mechanics and debris modeling. Astra a commercial software for space debris risk assessment and mitigation. 8. Ethical and policy considerations. Space debris is not just a technical problem, it's also an ethical and policy challenge. Responsibility Who is responsible for cleaning up space debris? Should there be international agreements on debris mitigation? Sustainability How can we ensure the long-term sustainability of space activities? Weaponization The development of active debris removal technologies raises concerns about potential weaponization. Enforcement How can debris mitigation guidelines be effectively enforced? 9. Conclusion. Space debris is a serious and growing threat to the future of space exploration and utilization. By understanding the sources and types of debris, developing accurate risk assessment tools, and implementing effective mitigation strategies, we can work towards a safer and more sustainable space environment. The code examples provided here are a very basic starting point for exploring the complexities of space debris modeling. For real-world applications, you'll need to use more sophisticated tools and techniques and stay up to date on the latest research and policy developments in this field. Further steps Learn more about orbital mechanics Study Keplerian elements, orbital perturbations, and coordinate systems in greater depth. Asterisk experiment with orbit propagation software. Asterisk try using Orbital or Astropy to propagate orbits with different perturbation models. Asterisk study conjunction analysis techniques. Asterisk research the statistical methods used to estimate collision probability. Asterisk follow space debris research. Asterisk read papers and attend conferences on space debris mitigation and removal. Remember to always use reliable data sources and validated models when performing space debris risk assessments. This is a critical area of research and development that requires expertise and careful consideration. Good luck.